Can you hear me? Uh, yes, I am speaking, but I was writing a message, so that's why I wasn't speaking. So, let's wait for 2 more minutes and we will talk about the solutions for the problems given in today's contest. So, these were the problems, and I'm going to explain for each problem my approach and also the solution and code. Also, by the way, you can also watch this screencast. Actually, is it a? I think I should just post on Code Forces as well to get more attention. Okay. Yeah, I wasn't talking. Now I'm talking. Sorry about. Am I a hacker? I will let the audience decide if I'm a hacker or not. Okay, so it's 45, I think. Now I think we can talk about the solutions if you want. Sorry about that. Okay, so it seems like. Okay, so let's start with the problem A. So in problem A, we are given an integer x, and we need to find how much do we need to add up to x such that x becomes a multiple of 100. And if x is a multiple of 100, then he has already gotten the prize for collecting x coins. So for this problem, it's a quite easy exercise of mathematics, and you just have to print n minus n mod 100. Quite easy. You just have to write this, and you should be done in 1 minute or so. Is everything alright so far? Okay. I will be waiting a bit. Okay, let's go now to B. We call a string hard to read when its odd position the characters are all lowercase letters and when the even position characters are all uppercase letters. Once again, this problem is really easy, and we just have to do one for loop where we basically check what we are given in this statement. Like if it's an even position, then we should check if it's an uppercase letter, and if it's an odd position uh, string letter, then we check if it's lowercase. Again, a really simple exercise, and it should take a few minutes at most. I guess there won't be questions for this one either, since usually in AtCoder Beginner Contests, the first few tasks are meant to be really easy. So they shouldn't be difficult for people who know how to code. You just need to know how to think at them a bit and you will be fine. Task C now, and then we will talk about this, since it seems that it's a task which is really demanding. Now, for C, C is a bit harder, but again, not really hard either. Like, we have an integer n, and we have k as well. And we need to compute these values for each step, and actually for k steps. And since k isn't too big, we can literally simulate the process. The way we do this, and I'm going to show my submission, is by basically finding the digits of n and sorting them in increasing order. I will keep this for later usage. And for each step, I'm finding the digits, sorting them, and I compute the smallest and the biggest number we can achieve. And then I update the value of n based on these two values. Again, something really easy. It takes a bit more time to figure this out, but in short, you just had to simulate the process. Now let's go to problem D. For problem D, we have a string x and an integer m, and we have to find the greatest digit in x, and based on that value, we need to find how many different integers not greater than m can be obtained by choosing an integer not less than d plus 1 and seeing x as a base n number. In other words, we need to find how many bases are there such that the number written in that base is not greater than m. And this problem has been quite difficult compared to the other problems in this contest because both the implementation and the thinking part were not really easy. And even I managed to get 2 wrong answers on it because I had some bugs in my code. Now, for this problem, the idea isn't that difficult, like the first part of the idea. So what we have to do is, firstly, we need to see if the current number is bigger than m in base d plus 1. Like if this is the case, then the answer is obviously 0. Now, otherwise, there are two cases. If the length of the number is 1, then we need to check out basically whether x is smaller or greater than m. And actually greater here. And here the answer is 1, and here the answer is 0. Now, if the length is bigger than 1, the way I did this is by binary searching the base, such that if we write x in base k, it's gonna be smaller or equal than m. And if we're gonna write it in base k plus 1, then it's gonna be bigger than m. So we need to search the value of k in this case. Now, since k has to also be bigger than d, this is gonna be the lower bound of in our binary search. And what I chose as an upper bound was something like 2 to the 60, which is 10 to the 18 roughly. And the reason why I did this is because I saw this number here. Like I saw 10 to the 18, so I said like, look, we can add the upper bound to be 10 to the 18 because our binary search would do 60 steps at most, which is pretty reasonable. Now, probably the most difficult part of this problem is the implementation part. And in this case, even though I use C++ most of the time, I decided to use Python for this problem. And I have a good reason why I did it. Actually, the reason why I used Python was because when it came to divisions and to multiplications, I realized that I would have needed big integers. And as you know, in C++ we don't have big integers. So I decided to use Python for this because it was way easier for me to come up with multiplying stuff like if it was on C++ rather than writing a long big integer code and explaining why do we need big integers and stuff. So here I found the maximum number, maximum digit from x. If the length of x is 1, then we find the value of x and we check if it's bigger or smaller. And otherwise we do the binary search. Again, the lower bound is the maximum digit plus 1 and the upper bound is 2 to the 60. And here in the binary search we are searching if the number written in base mid is bigger or smaller than m. And if it's smaller or equal, then we update the answer and we increase the lower bound. Otherwise we decrease the upper bound. And at the end we need to print the answer. I didn't get the meaning of seeing x as a base 10 number. So basically what does that mean is that usually we write the numbers in base 10. Like literally every number we write in real life. But instead of seeing it as in base 10, we see it as in base 10. What does this mean is that if we have a series of digits, dk minus 1, up down to dk minus 2, and down to d0. And if we write it in base n, it's gonna be equal to dk times n at k minus 1 plus actually it's gonna be n to dk plus dk minus 1 times n at k minus 1 and so on down to d0 times n at d0, but this is 1. So I could have ignored it. So this is like writing a number in base n. You could have checked this with these samples actually. Like you could have converted 999 in base 10, in base 11, in base 12, since there are base converters as well. Like you could have done something like this from base 10 to 11. Let's say you have 99. And no, actually it's like reverse. Like we need to see what swap actually. Actually, we need to convert 999 base 11 to base 10. And this would have worked. Like if you didn't know what does that mean. I mean, the reason why I used Python was because I was lazy to implement it in C++. I could have done it in C++ as well. But I realized that this number is gonna get quite big, and this one as well, so I just wrote it in Python because it's easier. And it makes my life easier. And we need as programmers to get our lives easier when it comes to writing code. Now, let's go to E. So in E, we basically have a shortest path problem where we have a graph with n cities and m railroads. And we know for each railroad that we have a period. Like the trains are leaving from cities A and B periodically, once at ki seconds. And we also know that the train takes t seconds. And we basically have now to do a shortest path between city X and city Y. Now, this problem is going to become a simple Dijkstra problem after we realize these two observations. The first observation is that the shortest path is the most optimal. So, like for each city, we need to find the shortest path. We don't really care about that property that if you like waiting for, we don't care that we have to wait for the train a bit. As long as we get there as fast as possible, our chances to get the fastest train become 100%. Like, let's say you go from city 1 to city 3, like this. We assume that these are the times you need to spend. So, like, let's assume this one is the fastest. So this one is the shortest one. It has length 5, and this other one has length 6. We don't care now if the train leaves at time 9. Because no matter if we get there in 5 or in 6 seconds, we get there at time 9. But let's say if the train left after 5 seconds, then this path is way better than this one. Because for this one, we would also have to wait for more seconds in order to get a 10. So again, we need to find the shortest path for each city. And after processing this new definition of distance and time, the problem actually becomes a shortest path problem, which is like really obvious to implement. Again, we add the edges in the graph, and it's basically a Dijkstra implementation. You only need to deal with modifying the time. Like, the time isn't actually the time given in the statement, but a sum between the time given in the statement and the time it takes for the train to start again. So again, not too hard either. Like, you only have to see that it's basically a Dijkstra problem. So that was task E, sorry. Now it's task F. For task F, this was also pretty interesting. So we have n kinds of materials, and the magic we know the magic power of each material, and we need to choose a subset of materials such that we get to some x as fast as possible. And x is quite big. Like, x is at least bigger than the sum of all the AIs, because n is 100 and AIs are up to 10 to the 7th. So when you multiply these two, you get 10 to the 9, which is smaller than the smallest value of x, which helps us quite a bit, as you will see later. Now, how did I approach this problem? Well, you can also see that in screencast, but now I'm going to explain the solution. So what I did was basically, I realized that I can't really do any brute force because n is too big, but n wasn't that big either. So what I did was fixing the number of materials we are going to take, and for each number of materials we are going to take, I did a knapsack. And that was enough, actually. Like, for each number of items, uh, so I have this DP recurrence. DP of ijk is going to be the biggest sum we can get if we took j items among the first I items, and the remainder of the sum when we divide by the number of items is going to be k. So let me write it once again. So dp of ijk is the maximum sum of j items taken among the first I items. Uh, if reminder is k, and we fix the number of items. Now, since we agree that we should fix the number of items, now I just run a normal knapsack. It's literally the knapsack code. Like for each state, I check if it was visited before, and if it was visited, I update both states in case I visited the next one, or in case I take the next one, sorry, and in the case I don't take the next one. So it's literally like in knapsack, when you take a new item. And at the end of each step, at the end of DDP, I just check if I have an item, if I have a subset of items, such that it's a reminder when we divide by items is equal to the reminder if we divide x by items. And again, simple math, we just need to drop from x the maximum sum and divide it by the number of items. Since in the statement they say that at each second you get k more power. So that's why I fixed the number of items. Is it everything clear? Oh, you didn't get D yet. Why are we using binary search? The reason why we are using binary search, so this is for D, and this was for F. For D, why we are using binary search is that if we convert a decimal number to a base n, the number is going to be, actually no, if we convert the base n to decimal, for the same number x, so if we fix the number and we convert it from base n to decimal, the graph of the function is going to be increasing. Like, it's going to increase in some way. I don't know exactly how. It's probably linear or something. But actually not really linear, but more like this, I don't know. Because what happens is that according to the formula I have written previously, we need to increase the exponents. Like instead of n, we're going to have n plus 1, n plus 2, n plus 3, and so on. And for this reason, the numbers are going to always increase. Because we have the same number written with the same digits, but instead of n as being the power we raised it to, it's going to be n plus 1, n plus 2, and it's going to be bigger. Okay? And about my contest, personally, I am decently happy with my performance. Like, I did fine when it comes to solving problems. But I got several wrong answers because of silly reasons. Like for A, I forgot to delete a template, as you can see in the screencast as well. And for D, I forgot the corner case, which cost me one wrong answer, and I was also printing something I shouldn't have printed. So my position would have been higher. But given that I am not really doing a lot of practice these days anymore, overall I did fine, I would say. Like both D and F were not too easy, in my opinion. They were pretty fine for this kind of contest, I would say. Do you have any other questions? If not, then I guess I won't be keeping this live stream for too long since I discussed what I had to discuss. And I will keep it for like 2 more minutes in case uh, something happens. Seems like nothing really happens anymore. So I guess I'm done for now. I hope you enjoyed the live stream, and I wish you good luck, have fun, and I hope you will solve these problems and learn new things out of what I said. Until the next time, stay safe, stay healthy, good luck, and goodbye.